Good evening, everybody. My name is Kristen Fletcher. I'm the Adult Programs Manager here at the Hailey Public Library, and I am so glad that you could join us tonight for this very special presentation. Tonight, we're pleased to partner with the Idaho National Laboratory to host the last of 3 talks on the site's cutting-edge research. Tonight's talk is Powering the Mars Rover Perseverance, and our presenter is Kelly Lively, the INL Project Manager for NASA Space Missions. For tonight's talk, I want to give a special shout out to 3 people. A real thanks to Paul Reese, who attended a tour at INL, I think about a year ago, and came back and said, hey, do you know all the cool things they're doing out there? I really think this would make a terrific series of talks for the library. And so he put me in touch with Abby Todd and Lori McNamara. And I want to give a shout out to those fine people for really just being terrific to work with. I've worked very, very closely with them, and it's been a real pleasure. So it is my pleasure to introduce Kelly Lively. And I mean, at the beginning, what a wonderful name, Kelly. I mean, that's just a terrific name. So she is the Isotope Power Systems Department Manager at the Idaho National Laboratory in Eastern Idaho. She has served as the department manager since 2007 and is the INL Project Manager for NASA Space Missions. Most recently, she managed the INL team that provided a radioisotope power system for NASA's Mars 2020 mission, powering a land rover named Perseverance for a 7-month journey to Mars. Perseverance took off from Cape Canaveral on July 30th and is scheduled to land on Mars on February 18th. Kelly holds a bachelor's degree from engineering at Idaho State University in Pocatello. And I just want to thank you very much for taking the time to join us, Kelly. And we're all really looking forward to your talk.
Well, I hope I can do it justice with that wonderful introduction. And I have to say, I kind of want to move to Hailey just to enjoy your library programs up front and personal. So it sounds like you guys have quite a program there. Very impressive. So let's just get right to it. Radioisotope power systems, that is me. I'm often referred to as the space battery lady, although this is not a battery, it is a generator. So our programmatic mission is to fuel, test, and deliver radioisotope power systems and related technologies for use in remote, harsh environments such as space. Radioisotope thermoelectric generators, or RTGs, are a type of radioisotope power system. They're an electric generator that convert heat, which is generated from the radioactive decay of plutonium oxide, which is the radioactive fuel, and it's converted into electrical energy using thermoelectric devices. Here's just a little slide of a thermoelectric circuit. On the right-hand side of your screen, you'll see an illustration of the latest nuclear power system. It is a multi-mission radioisotope thermoelectric generator, an MMRTG. It's why we have acronyms. We have the tendency to have really long names for things. But this is a 120-watt electric output nuclear power system. And it works on the Seebeck effect. And that phenomena says that if you take dissimilar materials and you connect those materials at junctions and you apply heat at one junction and cold at the other junction, then that will drive that circuit to create an electrical current. And that it's a very simple, it's a very simple and old technology, as it were. This program has been in effect for about 60 years now. They're very reliable and used really where the sun doesn't shine. There have been many radioisotope missions, 27 to date. starting in 1961. And I'm going to talk to you about 3 of those missions today and some future missions. So specifically, New Horizons, which was a flyby mission that launched from Earth in 2006. It was a 300-watt electric system. And then the Mars Curiosity rover, which was launched in 2011, and the Perseverance rover, which is the most recent one that launched in July of this year. So just so you're aware, Kelly Lively doesn't do all of this work on her own. We work in collaboration with 2 other national laboratories. So we're 3 laboratories. We're 3 national laboratories in the DOE complex, which is comprised of 17 national laboratories. And DOE is committed to provide these nuclear power systems for NASA deep space missions. Now we do terrestrial missions as well for the Department of Defense, but I'm not at liberty to really talk about those so much, but just know that we don't only do space missions. But I will, a shout out should go to Oak Ridge National Laboratory, Los Alamos National Laboratory, which we commonly refer to as ORNL and LANL, and then INL. So Oak Ridge, we give them credit for making the Pu-238 isotope powder. They make that powder and then they send it to LANL and LANL takes that powder and they make it into a ceramic pellet. And then that ceramic pellet is welded inside of an iridium cladding. So it's encapsulated by iridium. And then it is shipped to INL, where we take and assemble those fuel clads inside of general purpose heat sources and then assemble those inside of these power systems. And these power systems are made by private industry. And I'm going to go through what you would see in our nuclear facility and what we do with those pellets, how we get them and what we do with them. And then finally, once we build and test the power system, we transport it down to Kennedy Space Center, where we do some ground operations. I'll show you some pictures of that. And then finally, mate the power system to the rover, in this case, for launch. So here's some pictures of my team. This was the first and the last power system, and here's just some vital statistics of them. So in the left-hand corner, you see the spacecraft New Horizons. Now, I am the cute second one from the right, in case you didn't recognize me. And we're standing next to the New Horizons spacecraft. Now, it was really surprising to me that it was so small. Now, I'm in that picture, I'm 5'6" and 150 pounds. I'm not so light now. The mission for Perseverance is in the lower right corner, and I'm standing behind our power system. I'm still 5'6" tall, but I'm like 170 pounds. So anyway, just to get a perspective of how big these, or how small I think these units are. So the vital statistics, the one for New Horizons, it's a 300-watt electric class system, and the white one for Perseverance is a 120-watt electric system. And it uses a little less than half of the plutonium oxide fuel that the larger system uses. Different thermoelectric materials because they're going to different places. Okay, where do we do all of this fun work and handle radioactive material? Something you will not find at Walmart, I guarantee it. Otherwise, I'm going to be in big trouble. But anyway, so here's some pictures of some of the places that we work at Idaho National Laboratory. We work at the Materials and Fuels Complex. In the Materials and Fuels Complex, we have a nuclear facility and a non-nuclear facility. Everything that utilizes the radioactive material we do in the nuclear facility. It's called the Space and Security Power Systems Facility. We are one of 13 nuclear facilities at the Materials and Fuels Complex. And you'll see in that center picture, we're behind 2 fences there to get into our nuclear facility. And what you don't see is we've already gone through 2 fences to get to these 2 fences. So we are definitely in a very secure, protected area. And the reason that we do all of our work in a nuclear facility is that it is our responsibility, in accordance with the Code of Federal Regulations, to protect workers and the public from any radioactive release of material. So these buildings have inherent engineered systems in place to do just that in case there is some accident that might happen. So I have to admit, I feel safer working there than I ever did when I was chasing parts for Rush Auto Parts in Idaho Falls, me driving around as a teenager, and also at Pizza Hut, which I inadvertently tried to burn down one day. So, as far as I'm concerned, I am a much better, safer place dealing with radioactive material than I was a hot oven. But anyway, I digress. So we have several capabilities in these laboratory spaces, and I'm just going to show you some pictures of those. I'm going to take you through the process as in the same order that we complete it, so you can kind of follow along with me like a little storyboard of what we do. Hopefully, storyboard, B-O-A-R-D, and hopefully you won't be bored, B-O-R-E-D. So the picture that you see here is us receiving the 9516 cask, where once disassembled, we will find those iridium-clad fuel pellets. So the cask is in the upper right-hand corner. You see nuclear technicians rolling it in with a pallet jack. That's about 2,500 pounds of metal, and it's a stainless steel cask in the middle, and inside of it contains a nested series of stainless steel containers. And that's how we transport over the highways radioactive material, or this particular radioactive material, to our site.
Kelly, I have a quick question for you. So when we rarely see a flatbed with radioactive symbol on it, could it be this product coming to the INL?
It would not be on a flatbed truck. So
Okay.
these are transferred. Oh, sorry, that's my ringtone. It sounds fancy, doesn't it?
Sounds out of space.
It does. Sorry about that. Let me tell him I can't talk right now. It's one of my peeps. Anyway, no, these particular ones would be transported by the Department of Energy in what is called secure transport. And so they contract the National Nuclear Security Administration, NNSA, to transport this particular fuel. Now, you will see radioactive shipments on a flatbed truck, and ordinarily the material would be transported in some type of shipping cask. And they have to go, they go through lots of testing to provide a safe and secure transport of radioactive material. So you will see those certainly on a flatbed truck,
Okay.
just not for Kelly's program.
Okay. And then we do have a question in the question box. Thank you very much for posting that. And we have a question from Hayden.
Yes.
It's, what are the advantages of using nuclear power rather than power types such as solar? Does nuclear power tend to just last longer and be able to last at night?
Hayden, that is an awesome question. How old are you, Hayden? I have to ask, so maybe you'll pop up the answer to my question. But these are designed.
Hayden is 12.
He's 12. Oh my goodness. Yeah. Very intuitive.
Great question, Hayden.
Yes. So these, and you'll probably have to ask me the question because I'm 56 and I might not be able to remember both parts, but these are designed for a 14-year lifespan. And the reason that we use these, okay, so the answer to the first question is these last for decades. Some of the earlier space missions, such as Voyager 1 and 2, they were launched in the late 1970s. They are still traveling in, they've gone outside our solar system, but they are still communicating information back to Earth. So these will last decades. The radioactive fuel has an 87-year half-life. So in 87 years, it will have half of its energy left. And then in 87 more years, it will have a quarter of its energy left. So these simply last for decades. They have no moving parts in them, and they are very reliable. The reason that we use nuclear power for these deep space missions is because literally you can't get enough sunshine to efficiently charge solar panels to produce power. So some of the advantages are, such as on Mars, we are able to send these larger rovers to Mars, and they can travel in places of shade. They can travel at night. They can and they can photograph at night and do their science at night if they want, if the scientists want to do that. So they can travel around and they're not relying on the sun. And also the environment on these planets are such, especially on Mars, it's very dusty there. So with solar panels, you have the risk of them getting so dusty that you can't use them. They won't generate power anymore because they can't, because of the dust layer on their solar panels. Now, I do think that we ought to send one of these nuclear powered rovers over there and blow the dust off of them and go about their way. But I will say that the Mars rover and Perseverance rovers, they are the size of Mini Coopers. So they are the largest rovers on Mars. There are a couple of smaller rovers that I could refer to, Spirit and Opportunity, very, very small rovers. They're solar powered rovers, but let's see, Spirit got stuck on a rock it was traveling along and rock not seen because of the systems it had on board, inadvertently driven over a rock and got high centered. There are t-shirts out there by the Jet Propulsion Laboratory who designed that little tiny rover that market Free Spirit on those. And so I think everyone should have one of those. I think that's adorable. But those are just some of the problems with solar panels. They certainly have their use. I'm not saying we shouldn't use solar, but I think it's good in the NASA portfolio to have different power options. Did that answer your question? That was like really long-winded, Hayden.
No, I think that was a perfect answer. And I'm just going to chime in. I was reading, I think it was in Sarah Johnson's book, one of the rovers wasn't taking pictures because there was dust on the camera. And then a windstorm came and blew the dust off, and it was able to get enough power to take then a panorama shot of, because it had gone way out into Mars someplace. And was able to take this series of panoramic shots that they wouldn't have been able to get if the dust hadn't been blown off that solar panel. But,
oh, that's awesome. Yeah, that's
so
awesome.
we have a question from Piper, age 9. And I don't know if Piper is a boy or a girl. The question is, how many people does it take to make these?
All of them. There are hundreds of people involved. So we have people at Oak Ridge making the fuel. You know, those they number in tens. There are just 70 people in the program at my national laboratory that is involved in this program. You have the people that build the power system. That's private industry. You have people that designed and built the Rover. For this case, it was the Jet Propulsion Laboratory. You have the people that build the rocket, United Launch Alliance, they build the Atlas V rocket. You have all of the subcontractors that build and ship the different parts of the rocket. So they number in hundreds, maybe thousands of people that literally are involved in the success of these missions.
Wow.
Multi-millions and billions of dollars.
Mm-hmm. Well, and then Paul asks, all of a sudden we have a little flurry of questions. How much does one of these units cost?
The power system alone, you can buy fully fueled, and just because you guys are so kind and interactive, I'll throw in delivery for you for a mere $74 million.
Okay, all right.
You will be the proud winner.
Well, that's all.
For me, and a visit for me.
That's all the questions we have right now. So please continue on with your slides.
Okay, we'll continue through the process. This is inside our nuclear facility, and here you see a glove box. If you've not seen a glove box, you may have seen one perhaps at a hospital. They have them they use them in other applications, not just at nuclear facilities. The glove box is in the upper right-hand corner. We do all of our work inside glove boxes until it's a fueled powered unit. This particular glove box we use to assemble the fuel clads from LANL into these general purpose heat sources. You see an assembly picture there on the left. The red dots indicate the fuel clads. There are 4 fuel clads that are inserted into a general purpose heat source. And you see one in the next picture on the bottom, the second picture from the left. You see a partially fueled general purpose heat source. And then you see the next picture, all of these next 3 are inside that glove box, but you see some of the fixturing that we use to rotate the general purpose heat source and assemble those fuel clads in there. And then the last picture on the right is a quality assurance inspector and a nuclear technician, and they are most likely looking for serial numbers. So this is about a 200-page step-by-step procedure that is used to assemble these. It takes us about a 14-hour shift just to open the fuel clads and then fuel one of these general purpose heat sources. As I mentioned, these power systems come to us from private industry. This is actually the Curiosity power system that was delivered to us from Teledyne Energy Systems and Aerojet Rocketdyne. But the Perseverance power system looks exactly like this. And you just see nuclear technicians unpackaging it from its shipping box and placing it on a transfer cart that we use to roll it around our nuclear facility. And we would roll it right over to this large glove box. It's a mini hot cell, actually. And you see in the bottom center picture, the nuclear technicians are inserting it inside a door. And this is where we'll take those general purpose heat sources, we'll stack them up, and we'll insert them into the central cavity. So you see the hot cell and those manipulator arms. They're not robotic. Personnel, the nuclear technicians actually run those, and then there are arms inside that handle the equipment that is used to fuel these. Now remember, we're dealing with radiation and we're also dealing with heat. This is a fuel stack, so those 8 general purpose heat sources are stacked, and then they are picked up by a hoist on the inside of that little mini hot cell, and they're lowered slowly into the central cavity of the power system. That's what you see there. And then once that's done, and I'm flipping through these slides in seconds, it's a 30-day operation for that to happen. And then it comes out of that mini hot cell, and we do some other stuff to it. So first we want to make sure we have a good understanding of the radiation field that it's generating. You see it on its transfer card now. It is fueled, and you see a nuclear technician, the power system, and a plastic shield in between them. That shield is protecting the personnel from the radiation that the power system will always, always, always be generating. And it will always, always be generating electricity as well. Okay, so once we build these power systems, we want to test them, and we put them through a series of 4 tests that will simulate the environments that it will see during its mission life. This is vibration testing. It will simulate the launch environment and the landing environment that it will see. We go through mass properties testing. This is where we measure the center of gravity and the moment of inertia, because we want to just verify that when this is placed on the rover, it becomes part of a larger system. So now it's part of a system once it's installed that has to be balanced. Like you would balance a tire, these systems are balanced on a huge spin table. And the reason that they are balanced is that as they travel through space, you want it to be physically balanced so that you can get communications back to Earth from wherever it's going to. Our next test is magnetics testing, and this is where we map the electromagnetic signal that it is generating. It's generating DC power, not AC, but DC, and you just want to make sure that you understand what your system's generating so you can filter out that information from any onboard spacecraft measurements that are being taken, because certainly magnetic fields are being measured by these spacecraft or rovers when they get to their destination or even on their way to their destination. And then lastly, we perform thermal vacuum testing. We put the power system inside a vacuum chamber, and we pull a vacuum on it, simulating near Earth space environment of a vacuum. We can also make it cold in these chambers, but we make that environment in this 6-foot diameter by 9-foot chamber, and then we measure the power output. So now we know we've built it, we've put it through its acceptance tests, and this is where we will measure the power that will be the most similar to what it will generate in space. Yes, you have a question, I think.
Well, a couple. These are overview questions. Cynthia asks, is this unit fully funded by our government, or is it a combination of federal monies and private monies? I know you said there were private contractors involved kind of producing parts of it, but kind of where's the money coming from?
Apparently we have found our funding source, or someone that's interested in money. And Cynthia, you may be growing up to be a banker before this is all over with, but that's another excellent question. I've never been asked this question before. It is federally funded. We get our funding from NASA, which is a federal agency as well. So you can think of the Department of Energy as a subcontractor to NASA, and our job is to provide this power system. So we have, we being the Department of Energy, a bunch of subcontractors that we hire to build all of these parts. One of them that we hire is private industry that are not, well, they're funded federally, but they are a for-profit company, where our national laboratories are not for-profit. And so NASA funds the Department of Energy and its subcontractors to provide them with a nuclear power system. The Department of Energy and its contractors are involved because we can handle radioactive material. So that's why we are involved.
Great. And then Tallulah, age 6, asks, how many do you make in a year?
So Tallulah, I couldn't even type at age 6. That's so that's another excellent question. This is not a fast process. We are not a production company like you would be building refrigerators or rocket engines, perhaps, or cars. So these it's about a 5-year project to get the subcontracts in place and to build and test them and then deliver them. And so the whole mission for Perseverance for DOE to build this was a 5-year project.
Wow, great. Oops, wait a second. Oh, we just got a wow from Tallulah. and I think her mom's helping her out just a teeny tiny bit. So.
Oh, okay, we'll give mom credit for certain, but that's great.
So those are all the questions we have posted so far.
Okay, so once we get our power system fueled and tested, we are a full service laboratory, so we will deliver your power system to where it needs to go for launch. And this is in keeping with your questions that you had earlier about those trucks you see with radioactive material signs. So on the left, you see a standard size semi-trailer, and that is how we deliver your fueled power system down to Kennedy Space Center. In the next picture from the left, you see a yellow net. It is in front of a 9904 shipping cask. And the picture below it, you see the cask again, but you see it being disassembled. So inside that shipping cask would be the power system, and it is shipped vertically in that nested steel container. So that shipping cask that you see there weighs 5 tons. The power system weighs 97 pounds. So it is a Department of Transportation approved shipping cask, and these were specially designed for these power systems because they generate heat. At the surface, the temperature of these units are about 320 degrees now Fahrenheit. And so, you could handle them with oven mitts, and we do. We don't call them oven mitts because that's real. We call them thermal gloves is what we call them, but they're oven mitts. And so anyway, this is what we transport our power systems in. These casks have been drop tested. They're water cooled to help dissipate the heat. We also, not only are we escorted by a lot of guys with guns, I send down a 6-person technical team so that we can respond to any emergencies should there be any along the way. This is monitored all the way down there, and we have lights on the side of our semi-trailer that act as alarms, visual alarms to the truck drivers. And then we take it down there, we do some ground operations. I think I have some pictures of that later on in the presentation, but eventually we take it over to Cape Canaveral Air Force Station, and you see the launch pad that we have traditionally launched from up in the upper right-hand corner. You see a very tall building in the back, and then in the front you see the launch pad, and you see 4 pointy things up there, and those pointy things are lightning arresters. So you're at sea level at Cape Canaveral, and let me tell you, they get some lightning storms. So there they have lightning warnings. That is a huge thing. you've got lots of sensitive instrumentation, and they definitely take their lightning seriously. So you'll get announcements that say, you know, hey, lightning within so many miles, and then you perform your operations accordingly. You know, you don't want to be working on electronic stuff during a lightning storm. And then there's a close-up of that building in the foreground picture, and that is an Atlas V rocket, and it is fully fueled. And we will take our power system, which you see in the right-hand picture, and it's on a cart that will insert it onto the rover, which would now be stacked inside the fairing, which is the white part of the rocket on top. Note that there's solid rocket boosters on the bottom. So fully fueled rocket when we go mate that thing to the rover on the launch pad.
Kelly, I have two quick questions. If you could run the slide back. So the picture in the upper right-hand corner, where is it actually launched from? Is it launched from kind of inside the four pointy things, or is it launched from the kind of tall building kind of in that upper left?
Yeah, so the rocket's assembled in the tall building, and then it is literally moved by rail. There are railroad tracks out there, and it takes about an hour for it to get to the center of those four pointy lightning arresters, and it's launched from there.
Huh. And then Hayden has another question.
Hayden.
Thank you for answering my last question, but I have a new one. What kind of element and its isotope is the best for this kind of thing, and why is it used?
So the isotope that is used is plutonium-238. It's an oxide fuel, and it is used because of its half-life and that it generates heat. So it has a long half-life. It will last and produce heat for decades, and that's why it's used. And there are other isotopes that produce heat, but this one has a long half-life, and it's more, it's safer, or its radioactive strength is less than some of the alternatives, so it's easier to protect workers from its radiation energy.
Okay, thank you very much.
Okay, so some more pictures. Perseverance, it had other names attached to it. There was a competition of students from all over the world, K through 12, that put in names and justifications for naming it that, and NASA had a committee and they chose Perseverance. So there were some others. We got to vote, and so that was quite fun, but Perseverance was shown. And these pictures that you see were from Perseverance at Kennedy Space Center, and also at Cape Canaveral Air Force Station. So the top left one was at KSC, and it's in a clean room, and you see the rover being attached to the descent stage. So it's a big sky crane that lowers the rover to the surface, and you'll note that the rover is upside down. Also, it's kind of cool. You could have sent your name to Mars. So you see on the bottom left there are the names of 10 million people throughout the world that are etched onto 3 microchips that are on their way to Mars. On the upper right-hand corner, you see the ULA, United Launch Alliance booster. So that's one of those booster rockets that was used for this mission. And then in the lower right-hand corner, you see just another view of that rollout of the Atlas V rocket onto the launch pad. We also do what's called a hot fit check. So in that clean room facility at Kennedy Space Center, one of the very first things we do is put on flight hardware, and it is attached to the rover for the very first time. The rover will be powered by nuclear power. So really an exciting time for us. Not that we haven't tested, a lot of times, but this is the first time it's powered by nuclear energy, and I have to admit, I shed tears every time, it turns out. I shed tears at this point, I shed tears at the rollout to the rocket and to the launch. So, you know, there you go. I don't know what it is about it, but and then you see that picture of our team again, a very proud moment. This will most likely be my last launch and space mission, as I'm looking forward to retirement here next year. So very surreal, and it was so very cool for me to see all of these young guys in there and doing this work and learning, and the smiles on their faces, getting to be just a little part of history. So extremely satisfying work for me. Here's another picture of different stages of the rover. So the fairing is in the lower right-hand corner, and that is where the spacecraft that contains the rover will be encapsulated and make its journey over to the launch pad on a semi-trailer flatbed. In the upper right-hand corner, you see a picture of the rover before it was stacked inside the spacecraft. So lots of layers there. The center picture is the rover. It was just delivered to Kennedy Space Center, and they, you know, it's unfolded itself. And we're getting ready to do operations on it. So the Jet Propulsion Laboratory, where it was built in Pasadena, California, it was one of, I think, 47 shipments of equipment and materials to Kennedy Space Center. So quite a big deal. You know, it makes my little truck with one cask on it look pretty benign. And then on the lower picture, you see the spacecraft and the rover, and or what's going inside the spacecraft. So it will be encapsulated with the spacecraft, but everything's stacked in that picture. And then the picture of the building is just the building that all of this work was accomplished in at Kennedy Space Center. And then
can I ask you a quick question? Sorry, because it has to do with the packing and everything. It's really interesting how it gets nested in, and that lower left-hand picture, I was trying to figure out, I guess the little round things are the wheels on that lower left picture?
Yes, they are. The round things wheels, they're titanium wheels. Now, the not to be confused with the wheels on the stand that's holding it.
Correct. Right.
Okay. Yeah.
So Carter has a couple of questions, or actually, I don't know if it's Tallulah or anyway, a couple of kids have been asking questions. So, oh, I see, it's Piper. How big is the rover when it's finished? And then kind of a follow-up question, how big do they get? Are there different sizes of rovers?
Yes, there are many sizes of rovers. There's actually a Mars exploration program that NASA has, and there are rovers of different sizes from different countries. So we are not the only ones roving around Mars, I might add. Perseverance is about the size of a Mini Cooper. It stands, I think, a little over 6 feet tall, and I believe it's about 6 feet in length. But you know, it's not huge by our standards. It's not a Cadillac or a van, but it's the biggest rover that is on Mars. A Curiosity is about the same size, but Perseverance is even a little bit bigger. And was there another question? Did I answer all of her questions?
They kind of went together, yeah. Mm-hmm.
Okay.
So you're good to go.
Okay, great. Okay, so we'll go on to about launch minus 9 days, and we load up our power system and we take it by truck over to Cape Canaveral Air Force Station from Kennedy Space Center. And you can see in that center picture, we actually put it on the apron in front of that building, and then we lift it up to the MMRTG level, and it's about 200 feet, and it's hoisted up on the outside of that building. We landed on the mezzanine, which is in the second picture from the right. You can see a little bit more close up of it, but you can see it way on the very top mezzanine up there near the tippy top of the fairing on the rocket. And then you see that, I guess I'm just infatuated with that insertion cart. You see that MMRTG on that cart, and it just amazes me every time that they, an engineer designed this thing, and it was manufactured, and there are people that handle it on the T-handle end of it, and just slide it right up a chute to connect it to the rover, which by now, if you remember, is upside down inside the spacecraft, inside the fairing, and the fairing is now 200 feet in the air on top of this fueled rocket. Okay, so then is all we're waiting for now is the cruise to be over. We've done the launch, check. We are in the cruise stage, and then we're going to land and explore. So you see a center picture of the launch. You can see all the launch pads. I included a picture of Cape Canaveral Air Force Station, and you see all those different launch sites, and they're building more. Private building more. So SpaceX, Blue. Let's see, Orion. There's another one called Blue something. The name escapes me, but lots of construction going on there for launch sites and buildings. You see an illustration of the sky crane over on the right-hand side, and that's how it will be lowered down to the Martian surface. And this is only the second time it will be used. Previous rovers were landed by balloons, and so they would bounce around, and it was much more challenging to get them to bounce and stop where you wanted to explore. And so this is more exacting to place the rover where you want it. And the bottom picture is actually a selfie of the Curiosity rover. So it's, its first selfie, and it's made up of a collage of pictures, but you see our nuclear power system there in the back. It's kind of hard to see because the rover's mostly white. So the Perseverance rover, it's going to land on February 18th. So we'll be having a soiree and listening to the Jet Propulsion Laboratory and what they have to say as it's lowered to the Martian surface. And if you can imagine being the scientists or engineers that worked on it, and how exciting that would be to hear that it's going to land safely and that it's deployed and that it's operating. So those people have a few more months of stress to get by. I will say that the Perseverance rover, let me go back to it, is the second of 3 missions that are tied together. The first one being Mars Science Laboratory named Curiosity. And you see the power system there circled in red, because it's all about me, and I think that that's the most important part, but it's not. But its mission was to go to Mars and see if it could find evidence that life could have been sustained on Mars. And so they found microbes that were evident that life could be sustained there. They found lots of things, but that encouraged NASA to fund the next rover, which is Perseverance. It will be collecting soil samples and caching them in stainless steel tubes that are on its underbelly. And those will incite a third mission, which will be a sample return mission. So maybe in the not too distant future, we will get to lay hands on Martian soil. It'll be on Earth before we send people there. Yet we'll be able to do that. So that'll be exciting to see in my lifetime, I hope. So that's what's going on with the Mars Science Laboratory. The first mission, which is near and dear to my heart because it was my very first space mission, travels on into the Kuiper Belt. It was launched shortly after Pluto was named not to be a planet. There was a lot of uproar about that. And my spin on it is, wow, we thought the Earth was flat for a long, long time, and isn't it our mission to discover things? So why there was such a quandary over and arguments over the scientific community over Pluto being a planet or not, I'm kind of the opinion, I don't really care what you call it, go find out what it's doing and what it's all about. We can recategorize it. So anyway, it flew by its closest encounter to Pluto. It was a flyby mission on July 14th of 2015. And so it took 9.5 years to reach Pluto, even though it was traveling 33,000 miles per hour. Still continues traveling at that speed. And on New Year's Day of 2019, found its first Kuiper Belt object, which you see in that photo in the center. And it still continues to travel into the Kuiper Belt and investigate its next Kuiper Belt object. We're looking forward to powering a rotorcraft in 2026 launch. It is a rotorcraft that will be flown to Titan, a Saturn moon, and it's not very big, but it has 8 rotors on it. And that mission's principal investigator is actually from the University of Idaho, right here in our home state. So that was exciting, and I got to hear him speak, extremely passionate. And he was comparing the landing of the rotor on Titan to the landing of the Mars rovers. And he said it's going to be an hour and a half of mild concern versus 7 minutes of terror. And if you go Google 7 minutes of terror, you can see an illustration of the landing of one of the rovers on Mars. It's quite exciting. So it was just fun to hear him, but it will be another MMRTG, but it won't have fins on it this time for this mission. So, and we've already started that project. So you had asked, and we're probably going to go over a little bit. Is that okay, Kristen?
That is, because there are at least 2 questions that I know about. So
okay, so is now a good time to stop for a question before I go on to share with you about a little lively journey of how I got to where I am?
Yes, that was my second question. The first question is Matt asking, how will nuclear detritus, or the spent fuel, on Mars be addressed?
That is a good question, and I actually don't have an answer for that. You know, we're still trying to figure out, you know, exactly, you know, it's a dynamic process, meaning we're still learning about how to deal with nuclear waste here on Earth. So I truly have just not heard of any plans for nuclear waste. Now, I will say that we will not be generating nuclear waste on these planets because we will be sending up, like in the case of these rovers, you know, it's a power system and it's being used. So we don't have tailings from a reactor or from the process of making nuclear material. So the power system itself, I guess you could consider to be waste eventually when it's not being used anymore. So I don't have an answer for that because I just don't think that we'll, at least in the next few decades, be making things where we're creating waste.
Mm-hmm. Great, thank you. That was a great question. And I'm so glad you included this this slide, partly because we've got several young people listening, and I think it's going to be shared with other young people who may not have been able to join us tonight, but in the future in a classroom or in a home setting, because your own personal story is remarkable. And I'm just so glad that you're sharing it with us. So, so how did you get to here?
Well, I'm very humbled. I grew up in the Midwest. I like to say in the middle of a cornfield. I graduated from high school in Illinois, the same one my father graduated from, and I graduated with 34 students in my class. And my mom did book work for she and my father's private business. And I really wanted to be a certified public accountant. That's what I wanted to do. I just really appreciated and liked the fact that she worked with figures, and I liked it. She trained me to fill in for her, you know, so that I could help her out with book work in her absence. And I just really fell in love with numbers at that point. But it turned out 2 weeks after I graduated from high school, my folks moved to Idaho. The economy was bad, and so my sister and I, she's 3 years younger than me, we followed my folks out to Idaho. So I didn't even know if there was running water in Idaho. Not my first thought of where I'd like to move to, but so that was a challenge more so for my sister than for me because she was still just a freshman in high school. But anyway, we moved out here, and my aunt and uncle lived here, and they had suggested, hey, if you want a good job, go to work at Idaho National Laboratory. It wasn't called that back then, but it's what it's called now. And so, not really knowing anything about it, I got a job at the Naval Reactors Facility as a secretary just a year later. And I was a secretary and typed procedures for engineers. I didn't even know what an engineer was. And quite frankly, it turns out I didn't know what they were, even though I was typing procedures for them. But they were a subcontractor out here. And so they left and went back to the East Coast, and they're shipbuilders is what they are. And you know, when I got that job, I'm like, okay, they're shipbuilders. Their name leads me to believe Newport News Shipbuilding, that's the company I went to work for. That leads me to believe they I don't know, they write articles, I don't know what they do. But it turns out that they were training, or they were refueling a nuclear reactor that was in a submarine. And the Navy used it for training out here in the middle of the desert, unbeknownst to me. I had no idea. I didn't even know what nuclear power was, no less that there were 102 operating nuclear power plants providing power in the United States at the time. So I ended up going on April Fool's Day of '85 to be a secretary, again, typing procedures for engineers at what was known as Argonne National Laboratory. And so that's really how I got my first taste of engineering, because, you know, since my parents moved me to Idaho, I refused to go to college. You know, that I was teaching them a lesson, which turned out to only teach me a lesson. But anyway, I was making a good income at Argonne National Laboratory, and I ended up moving around a little bit, always keeping my eye open for opportunities to make more money, let's face it. And as I moved into a more technical position, being a quality control inspector in 1990, I really got a taste of, I wanted to do something more, and I felt that I was capable of doing something more technical for the laboratory, and that really piqued my interest. Again, working with engineers doing in different kinds of non-destructive testing and on experiments. So it turned out my academic alarm clock went off in '93, and I was nearing 30 years old, and said, you know, I need to figure out and explore and decide what I'm going to do when I grow up, because I think I'm grown up now. And you know, I wanted a different grown-up job than I had. And so I decided to go get my engineering degree. So I went to Idaho State University, ended up graduating 5 years later with a degree in general engineering, because that's what they offered, and an emphasis in electrical engineering. And so that's what I got, and absolutely enjoyed it. Realized when I got there that engineering had a lot to do with math, which it turns out I liked. Remember, I liked numbers, wanting to be a certified public accountant. So the math was great and ended up not being an obstacle. I took a math placement test, and lo and behold, when I got my high school education in that cornfield, I actually learned something. I placed in calculus. So I absolutely loved the curricula. But halfway through, and I don't suggest you do this, but halfway through, my biological alarm clock went off, and I had my 2 children when I was in college. So I'm working in the summertime to pay for my academic hobby of 5 years, and then it took full-time semester coursework, 12 to 15 credit hours in the fall and spring semesters, and graduated in 5 years and had 2 little babies when I came out. Then continued to work for Argonne National Laboratory in design engineering. So that is how I applied it in building systems, and then went on to, I had done some work for my current manager. He was impressed by that and offered me a position as a test engineer in the program that I'm in now. And then through each of the different space missions, it turns out, my responsibilities grew, and I went from a test engineer and the lead engineer for transporting the New Horizons power system down to Florida, and the lead engineer for ground operations down there. I moved from that to being a project manager and an engineering manager for the program, and then on to my current role for project manager for space missions. And also I'm a department manager. So I manage 20 engineers and 3 technicians and that laboratory space that's non-nuclear. And so that's what I'm doing now. Just finishing up with the Perseverance launch. So that was a great testament to the time that I've been in the program. And maybe on this April Fool's Day of next year, I will retire with 36 years of service. So that's kind of my journey. Always interested in math and science, but never knew ever that I would be involved with NASA and space. I was certainly not a space junkie. I would never have guessed that there would have been applications that we were involved with here in Idaho. So just remember, you don't know where a submarine's going to be, where nuclear power is going to be, or where NASA's going to be. They're all over the place.
Yes, and you don't really know where your career path may take you. I mean, it sounds like you were very satisfied in many of those jobs for quite a while, and yet there were new horizons that opened up in front of you, and you stepped forward into those new roles. So.
Yeah, and I think, you just have to always be looking out for managing your career and your life, and situational awareness is a great thing. And just don't say no to opportunities. I made many mistakes along the way and learned from them and moved on. And, I think it's just important that you keep an open mind and be able to work through those. I mean, I've shed many tears in the bathroom. I've walked a million miles around our site out of frustration, but, we all handle stress in different ways, and never let them see you cry. I'm admitting to it now. I feel that I've been in the job long enough that we all deal with stress in different ways, but absolutely worth every tear and every amount of stress to meet these goals and move into. I've just had a wonderful, wonderfully fun career.
Well,
You see my 2 grown children there. Where the picture where I'm sitting in my office in the green shirt. Those are my babies of 26 and 23 years old now. My son David and my oldest Kyla. She's 26. She's becoming a civil engineer, and my son is a motorcycle mechanic.
Well, very inspirational story, and I just want to turn to our audience and just see if there are any last questions before Kelly talks briefly about this last slide. So while she's talking about this last slide, if anybody has any last minute questions, please put them in the question bar. So.
Yeah, you can follow us on social media. And, I just realized at 56 years old, I was curious about what URL standard for. So I typed it out because I'll never remember it. But Twitter, I actually have my own Twitter account, although I'm not, I don't tweet a lot, but it's been kind of fun. But I would suggest, if you don't follow any others, if you go start a Twitter account and follow the Sarcastic Rover. So that's the Curiosity rover that's on Mars now, and she has quite a sassy little attitude. And so it's I love listening or reading her. I read her every morning, so she's fun. NASA.gov is an amazing website. If you go there, the pictures that are being sent back are phenomenal. And I just discovered a Facebook group that NASA, it's a NASA Facebook group, and the pictures right now from Earth of space, I don't know what's going on, but there are photographers that are posting pictures right now. So there must be something really interesting in space. I guess maybe planets close by that they're able to take these fantastic photographs, which I'm actually downloading, and I'm going to print a few out and put them on my walls in my home.
Well, thank you, Kelly. I'll just share with you a couple of comments. What a great talk. I am so glad Kelly shared her personal story. Cynthia says, we are clapping here. It's been an enlightening lecture. You're an amazing woman, wonderful role model for many young women. So,
oh, thank you so much. It's been so much fun. Life and work should just be fun.
well, thank you very much for taking the time and sharing this amazing project that you're involved with. And just a reminder to everybody that Perseverance is scheduled to land on Mars on February 18th, so mark your calendar. And we'll see you all later. Some more thank yous from other people as well. So thanks, everybody. Thanks for joining us tonight.
Okay, thank you. Have a good night. Bye.
Bye. So I think Eric or Jeff will be closing out except for staff. So we'll stay on a little bit longer.
Okay. All right, I'm going to sign off unless you need me for anything else.
Yeah, I do. Actually, there was something I wanted to say kind of when
sure.
our attendees are gone. We'll let our staff people tell us when that is.
Eric, can you end the session?
Laura, you hung in there. Aren't you tired of hearing me?
No, I'm still hearing, and he just did a really good job, Kelly.
Really, really a good job.
Yeah, I mean,
guys.
so fun to hear everything.
Oh, sorry.
Good.
Eric's computer crashed, so just so you know, we still have some attendees watching and listening.
Okay. Then the only thing I wanted to say was I mentioned to you before we started that my dad worked as an engineer at the INL. But before that, he was at Hanford. And one of the things that he did was he had an idea for creating protective equipment to help protect people. And he built the prototype for glove boxes.
Oh my goodness.
Yeah, and I've shared with Abby, and I think Lori's been there too, but growing up, I heard that my dad made glove boxes, and of course my only reference was glove boxes and cars. And so until my mom passed away when I was 45, and it was just a few months, not even a year before she passed away, that she shared with me, she said, oh, Chris, not glove boxes in cars, the ones that you put, you had to handle nuclear material. Well, I didn't know that.
Yeah.
So it was a real treat to see those, rubber gloves hanging down, ready for action, and know that my dad had a little part in that. I mean, he made it out of plywood. It was just an idea. It was a concept model that he and a couple buddies of his came up with, but it was just kind of neat to see here. It's kind of full circle with the work that you're doing.
Oh yeah, and I had seen them at work, and until I had my first child, it didn't really occur to me where I might see them. And she was born prematurely and ended up